In this video, we're computing a numerical approximation of the integral of tangent square root 1 minus x squared on the interval -1 to 1. And the reason that we're using a numerical integration approach here is because this function has no symbolic antiderivative. And specifically, we're going to use a trapezoid approximation, and we're going to use 200 trapezoids to get this done. And we can see already in the picture what a typical trapezoid would look like. I labeled the left side of it as xi minus 1. The right cut point for this trapezoid is xi. The height of the left side of that trapezoid would be f of xi minus 1. And the height of the right side is f of xi. And we're asked a whole series of questions here to help build up the summation notation that we're ultimately going to put into a computer algebra system. So in part A, we're asked for the subinterval width as a decimal. So we take the width of the entire interval -1 to 1. That width is 2. And we divide by the number of slices that we're slicing it into, which is 200. And this gives us a nice round number. That's exactly 1 out of 100, or 0.01. So each trapezoid is actually very, very thin, and the one in the picture is greatly exaggerated just so we can see it. In part B, we're asked to write down the ith cut point in terms of I. And I want to point out some of the notation here. Normally, the very left side of the interval we call x0. And in this particular problem, our starting point is x0 equals -1. And then the rightmost endpoint we normally call xn. And in this particular problem, n is 200. So that's our 200th cut point, and that's equal to 1. Now what about our ith cut point? All we do is start with the starting point, that's x0, and then we take I steps to the right, and the step width is what we call delta x. So plugging in the numbers here, my ith cut point, I start at the starting point, x0, that was -1, and I add to that I times the step width of 0.01. And it's probably nicer to write that as -1 plus 0.01 I. In part C, we're asked to express the sum approximating the integral in terms of xi minus 1, and delta x. So we're staying general in this step of the problem. We're not plugging in the actual function that we're integrating yet. And the area of a trapezoid is given by the average of the two heights. So that's f of xi minus 1 added to f of xi, all divided by 2. And then we take that and multiply by the width of the trapezoid, which is delta x. And then we need to set the starting point and the ending point of our sum appropriately so that we start with the right first trapezoid and end with the correct last trapezoid. And starting at I equals 1 is what we want to do in this case, because that would start me out with f of x0 for the height of the left side of the first trapezoid, f of x1 for the height of the right side of the first trapezoid. And then if I run this all the way to 200, that's going to give me 200 trapezoids. And the last one will have a left height of f of x 199 and a right side height of f of x 200. Now we can plug in our specific function f of x. That's the tangent of the square root of 1 minus x squared. So f of x evaluated at xi minus 1. Well, to find xi minus 1, I have to replace I with I minus 1 in my formula for part B. And I have the tangent of the square root 1 minus xi minus 1, which is -1 plus 0.01 times I minus 1, all squared. And then I have plus my function f of x, again, the tangent of square root 1 minus x squared, evaluated at xi. So I get 1 minus, and then looking back at part B, xi is a -1 plus 0.01 I, all squared. And then my delta x is 0.01. So this thing is ready to plug into a computer algebra system now, and we'll add up the areas of these 200 trapezoids and get a good approximation of the total area. And one thing I'm going to do to simplify what I'm typing in for the sum is I'm going to take these constants, 1/2 and 0.01. Those are common to every single term in the sum, so they can be factored out in front. And half of 0.01 is 0.005. So I'm just going to put a 0.005 in front of the whole thing, and then I don't have to write those constants for every term in the sum. And the technology that we're using for this is WX Maxima. That's a free open source computer algebra system. And so we've typed in our sum into Maxima, and I have that 0.005 out in front. And then we're using the command sum. I typed in my function very carefully here, the tangent of the square root of 1 minus the quantity, -1 plus 0.01 times I minus 1 quantity squared, and so on. And we're going to sum this up as I goes from 1 to 200. Now, in this case, it doesn't cause a problem, but if Maxima was refusing to give a decimal approximation, we could always put the command float around this entire thing and it would turn it into a decimal. But when we hit Shift-Enter, we get a decimal approximation. We're asked to do this to the thousandths place, so we get 2.167. And so we've answered the question, but I want to check my work with the built-in numerical integration algorithms in Maxima. And to do this, we'll plug in our original integral and use the quad QAG command to do numerical integration on it. So what we're telling Maxima is, give me the numerical integral with respect to x on the given interval -1 to 1. But there's one more thing we have to specify, and it's the algorithm number to use for quad QAG, and any number between 1 and 6 is perfectly fine for our purposes. And I hit Shift-Enter. And the first argument there, 2.1677 and so on, that's the numerical approximation given by Maxima. The second argument is the approximate error in that approximation. So you can see it's very precise. So to the thousandths place, we get 2.168 from the built-in numerical integration package. In other words, our trapezoid sum was slightly underestimating. And if we go back to our original picture, we can see why. This function is always concave down. So every time we draw one of those trapezoids, there's going to be a little bit of area that we missed above the trapezoid. So it's worth remembering that on an interval where a function is concave down, trapezoid sums underestimate. On an interval where a function is concave up, trapezoid sums would overestimate. Okay, so we're done getting our numerical approximation of this integral using a trapezoid sum. It was only good to the hundredths place when we compared to a more powerful algorithm, but we could always get more useful decimal places just by increasing the value of n if we wanted to. But not today, and we're done. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.